Here's another example for Bernoulli. The previous example we did, we solved for the velocity exiting from a tank subject to a gravitational field. In the second example, we're going to ask the following question. So Bernoulli example 2. Bernoulli example. Okay, so we're going to ask the following question. We have same tank, initially at a height capital H. Okay, so that's the initial height open to the atmosphere. And there's an opening or there's a valve that you open over here, and again the water flows out. So now the question is, how much time will it take for the tank to empty? So we saw a similar problem in the past where we applied mass conservation to get to this formula. So if we take this control volume, shown in red over here, just simply apply mass conservation for a fluid rho with a density rho. So mass conservation tells us, mass conservation on the control volume tells us that d by dt of integral of rho dv over the control volume plus the fluxes integral over the control surface of rho u dot n ds equals 0. And so there's the only output. We're going to assume that there's no velocity over here, so we're just only going to consider the exit velocity over here, v exit, okay, or ve. Another way to do this is to assume that the tank is closed, but that causes problems for the atmospheric pressure. So we're just going to assume that this is very, very slowly emptying. Anyway, so what this gives us is, this is d by dt, it's going to be d by dt of the integral of rho dv. So that's, since rho is constant, we get rho and dv. What is dv? It's the area of the tank. So if this is the tank area, a tank times h of t, okay, plus, now this integral is only going to give us the outflow at this velocity, at this exit over here. So that gives us v exit, okay, so it gives us rho v exit times a exit equals 0. And you cancel out the densities, and what you get is dH by dt is equal to minus v exit, a exit over a tank, okay? But that only is a function of v exit. So we don't know what v exit is. And this is where we can use now Bernoulli, or in other words, the momentum, a simplified form of the momentum equation to calculate v exit. Now we did this in the previous example, and to remind you, we just took a streamline from station 1 to the exit station. We're going to call it 2. The pressure over here is also P atmospheric approximately, assuming the height is small enough. So what that gave us was V exit is equal to square root of 2g times h. And in this case, h is going to be a function of t. If you want to see the derivation, look at the previous example. We just did P1 over rho plus V1 squared over 2 plus g z1 equal to P2 over rho plus V2 squared over 2 plus g z2. And then we canceled out the pressures. This guy is 0, and you get V2 is equal to square root of 2gh, which is the distance between the station 1 and station 2. Okay, so now we can take this guy and plug it in here. This is really great because now we use two of the laws that we've applied using the Reynolds transport theorem. We used the mass conservation law, and then we used the momentum law simplified to the Bernoulli through the Bernoulli equation. So this gives us dH by dt equals to minus square root of 2 GH, H is a function of T, A exit, the area at the exit over the area of the tank. Now, notice that dH by dt, there's a negative sign over here because the rate H is decreasing. So dH by dt with time is a negative quantity. So it's because H is shrinking. Okay, so now we can simplify this a little bit. We write this as minus square root of H times square root of 2G AE over a tank. Now I'm gonna take square root of H and write this in this form, dH over square root of H equal to minus square root of 2G A exit over a tank dt. And then we want to integrate this. So integrate. We're going to integrate this from H, the initial height, to 0. So we're going to write integral from H, the initial height, to 0, where the tank is empty, of dH over square root of H. And over here, we're going to integrate from the initial time 0 to t end, where the tank is empty. So t end is the time it takes to empty the tank. Okay, at the initial condition, we had the height h, minus square root of 2g AE over a tank dt. And that gives us 2 square root of h from h to 0 equal minus square root of 2g A exit over a tank t from 0 to t end. And if you do the solution, this gives you 2 square root of h is equal to minus square root of 2g, so minus square root of 2h, so 0 minus square root of 2h gives you minus square root of 2g A exit over a tank times t end. And we can use this to solve for t end. And just going to do some jumbling around. So t end, the negative signs over here, they become a positive sign. We multiply by a negative sign. And 2 over square root of 2 becomes square root of 2. Okay? And t end is equal to square root of 2h over g times a tank over a exit. And that is the time it takes to empty the tank. So we used mass conservation. We expressed the rate of change of the height as a function of the exit velocity, and then we used Bernoulli, or the momentum equations to along a streamline to find the exit velocity, and that allowed us to obtain this really cool result.